Can you hear me?
Yeah, I can hear you. Yeah.
Okay, fine. Okay, I'm ready when you are.
Okay, all right. So welcome to the meeting today. Thanks for everyone for attending. It looks like we have some people here who don't usually come. Tom, welcome. Thomas, welcome. And Susan's here. Dick, Yash, and Vinay, and Devansh are all here. So we'll maybe a couple more people will come in in the next couple of minutes, but
Okay.
so I don't know. I guess today we're going to have Richard
Somebody
Gordon.
just disappeared.
Some people, yeah, sometimes they have to reconnect.
Yeah.
So we have Richard Gordon today, Dr. Richard Gordon. He's going to talk about his work on diatoms, and he'll explain what those are and what the work is. It's on motion, so he'll be going through a very lengthy Word document to show pictures, a lot of explanation, and then we'll have questions afterwards. First of all, I should ask, does anyone have any issues or comments they'd like to make before we start?
Doug Thompson at the University of Manitoba is the gizmo maker there. He's got all the electronics, and he's teaching me a bunch of it.
Oh, good. Well, maybe you and Tom will do the diatoms. Okay, Bradley, you back?
Yes, sorry, my internet had a little bit of a glitch, but
we figured that out.
Yeah. So we have Emily Thomas joining us. She was a Google Summer of Code student in OpenWorm last summer, so welcome. So we got a couple more people coming in.
I better get started because I have an appointment at the end of the hour.
Okay.
Okay, so I'm going to start with a movie on diatom movement. You guys ready?
Yep.
Yeah. Okay, let's see. First of all, I have to do...
Share your screen.
Me? No, it's called presenting, isn't it? Okay, here's the button go for presenting.
Lower right-hand corner of the screen.
Lower right-hand corner of the screen. So you would think, there it is, present now. Okay. Your entire screen, yes. Okay, we'll do the entire screen. Okay. Will you allow people to see your screen? Select screen. I think it's screen 1, but we'll see. That seems to be it. Allow. Okay, good. Can you guys see me on the screen?
Yes.
Yes.
Oh, it says you're presenting your screen. There we go.
Yes.
Okay, now let me pull the movie up. I'm going to fill the screen. This is by Jeremy Pickett Heaps, who used to be at the University of Colorado, and he's now, I think, in Melbourne, Australia. Okay. And where's the, okay, come on. Where's the gizmo to start? Come on. There it is. It was off screen. Okay. Okay, here we go.
Double sticks. Enclosed in the rigid silica wall, diatoms cannot move like other small cells. However, some species move with a characteristic jerky, gliding motion, here accelerated about 25 times. Here, gliding is shown in real time in a mixture of marine species. This characteristic type of movement is generated by a mechanism unique to diatoms. Centric diatoms are considered immobile. However, some undergo a slight shuffling motion. This appears to result from mucin secretion through a special pore called a linear interstice, which may be the evolutionary precursor of the morphological feature called the wraith. With one exception shown later, pinnate diatoms that glide all possess the wraith, the name given to a very narrow slit through their valves. This pinnate area shows the common morphology of a central wraith running the length of the cell and interrupted with a central occlusion. The broken valves show how the wraith does go right through the wall, even though the slit is deeply curved. The morphology of the wraith is variable, but it usually follows the contours of the cell. In other species like this Sororella, the wraith runs around one or both edges of the cell. Here is the wraith of a live Pinnularia. Viewing it at high magnification and focusing down into the cell, we see active cytoplasmic transport just under the wraith slit. Staining cells to actin reveals two long bundles of actin filaments very close to the cell membrane along the wraith. When actively gliding Pinnularia are firmly pinned down, sticky elastic mucilage is secreted through the wraith. It accumulates while moving back and forth outside the cell. So, while mucilage oozes through the wraith, it remains attached internally to the cell membrane. Then this attachment site is moved back and forth by the adjacent actin filaments. In this slender nichia, the wraith lies along one edge of each valve in a narrow tube-like structure called a canal wraith. At high magnification, the canal wraith is indicated by the arrow. Cytoplasmic particles move rapidly along the canal wraith in both directions. This image is in real time with computer-enhanced contrast. The speed of transport inside the cytoplasm matches that of the mucilage just outside the canal wraith. One sequence is here to show the correspondence more clearly. Tiny polystyrene beads sticking to the mucilage outside the canal wraith act as external markers of this transport. In summary, gliding movement is generated by mucilage secretion coupled with cytoplasmic transport. This motile system can generate significant force. When this nichia gets stuck, the cell shows remarkable persistence in trying to move. The force it generates loads up water like a spring. This cell persisted in its behavior over 20 minutes. On some occasions, the force generated by the cell can permanently damage the wall. As noted earlier, there is one known exception to this protein mechanism, and this is understanding. It has no fatal through the dirty gliding motion of rapid penates. Both them double sticks. Enclosed in the
Okay, that's the movie. Now what I'm going to do is switch to my manuscript, which I'm going to have to show you in Word form because thanks to Bill Gates, there's all kinds of errors in trying to convert this to a PDF or anything else, which I'll have to fix by hand. Okay, so what I'm going to do is show you a bunch of models of how diatoms move. You shouldn't believe a word of what you just heard in the movie except for the pictures themselves. Okay. I'm taking what I'm calling a whimsical view of the whole process and the whole history of it, along with this diatomist cartoonist Steve Edgar, okay, who here's three diatoms moving on water, okay? Okay, so I'm just going to go here. First model, okay, was by this fellow, Henry Baker, and let's see, his work was 1753. So this is the first model from 1753. He looked at diatoms and he saw muscles sticking out of the ends, and basically suggested, he called them the oat animal, because it wasn't until the early 1800s that people realized these plants didn't chlorophyll inside them. So he called them the oat animal, and basically he described movements that are similar to somersaulting. Okay? And he saw muscles sticking out of the ends, protruding muscles. Okay? The other people who saw this, Andrew Pritchard, back in, let's see, let's Wikipedia, okay. Andrew Pritchard, this fellow, Jean-Baptiste Bory de Saint-Vincent, okay? And here, Jean-Francois Turpin, botanist, okay? The models of things sticking up and waving actually persisted till 1962 with Robert Yarosh, who proposed a model where the stuff that comes out of the diatom generates waves. Here he's showing a series of waves in the configuration for Basilaria. Okay, and he wrote quite frankly like people test this model. And he's still with us. He just had his 90th birthday recently. Okay, so the next model, the muscle model was the somersaulting model was criticized by these guys who decided that diatoms crawl like snails. They stick a muscle out and they can crawl around like snails. So we've got Ehrenberg, and on the right here, and Crawford-Young, okay, so we're up to, let's see, well, mid-1800s, 1838, okay, 1838, this. Okay, next. Well, they didn't like that model. He thought that the diatoms pull in water and squirt it out, basically acting like a jet engine. Okay, so this was his model for how diatoms move. Of course, we have modern jet engines. However, the history of jet engines goes back to actually to the 1700s. So the idea had been around, and so these guys didn't invent the idea of the jet engine. So the idea was to suck water in, pulled it out. Well, this was squelched quite mildly by Leslie Edgar, and Leslie Edgar showed that the rate at which the diatom would have to pull water in and squirt it out was enormous, and in order to achieve any motion at all, and it's obviously not what it does. Okay. Okay. The next model was started by Jabez Hogg. He was an ophthalmic surgeon, and he saw the diatoms sticking out. Here's his picture. Little oars, and the diatom rode with the oars, just like these ancient ships did with multiple slaves or others sticking oars out of a boat and moving it along. The name of those were quadrigs. Okay, well, he saw those oars and nobody else saw them after he did. And at the end of his career, he wrote a paper saying, well, he's probably wrong. However, maybe he wasn't so wrong, because the same Leslie Edgar made these pictures of these little fibers sticking out from the diatom along the slit, which was discovered later called the rafe. Okay, so other people who worked on this or for or against it. This is Pierre Marie Van Ermengen. And one of the things that supports this idea is, if you look here at the top here is a single fiber sticking through the rafe and presumably out a bit. So it's acting as if something is indeed sticking out and that they're in single file in the rafe. There's another rafe at the other end, which is not shown well here. Okay, so each diatom has two rafes, one on each shell. Okay. Okay. These guys, Max Schultz proposed that instead that diatoms move the way tank treads move. Okay. And Engelman, I think, supported this idea, and George Mueller went for it. And the idea here, well, I've taken two tank bodies here, put them together. So the idea is top and bottom of the diatom, you've got some sort of tank tread going, and they can work independently, and that's how a diatom moves. And some of the sketches here showed flow inside and out, and this would be the outside flow. Then they assumed that this stuff went in and went around somehow. Okay, so this is a tank tread model. Now, weirdly enough, in 2015, a model was proposed for another organism, bacteria, with a tread on it. And they literally have a thing sticking out here, which rotates and is carried on a track and acts, has a rotary motor next to it. These are all at molecular level. It's wrapped around the cell. The cell is sort of cylindrical with two spherical caps at the end. And this thing has a helical wrap. It's a single track around the cell. And here's a little rotating gear, which they think is a molecule, and there'll be a whole bunch of them, I presume, along here, which make this track rotate, and these little oars stick out. So this is a model for an actual organism in 2015. Okay. Well, the diatom, some diatoms actually move along and have no trail at all, and I propose as a model for that this character from from a Disney movie. Okay. Okay. Now, next model, which I thought I had invented, but actually goes back to 1883, is a capillarity model. And in this model, the diatom behaves much like a flame behaves. So if you look at a flame, what it's doing, it's got a pool of molten wax at the bottom. It has a wick, and it has a flame. And what's happening here is that the wax wets the wick, rises up the wick, and then undergoes a chemical reaction, turning it into a gas, which leaves the wick. And what that does is produce a continuous flow of the wax through the wick, lifting it up. Now, the force involved is enormous. If you were to try to grab on one of those molecules, you get pulled right up the wick. And then it changes chemical form, becomes a gas, and leaves. Okay? So the idea here, I've turned this diagram by 90 degrees to give the analogy. Here are fibers in the slit called the rafe. Okay? They fill the rafe, they wet it, but then they react by reacting with water, and they turn it into a form which can't wet the inside of the rafe. Now you have to sort of reverse your thinking here. The idea is there's some evidence that the walls of the rafe are hydrophobic, and this stuff that's in the rafe, I've given it a name in this paper. I call it Raphan, R-A-P-H-A-N. This stuff is hydrophobic, so it can fill the rafe. And by the way, so is wax. Wax is hydrophobic. It wets the wick and fills the wick and then burns off. So here's the idea that this stuff fills the rafe, which acts just like a wick, and then it comes out not by burning, but by hydrating. It becomes hydrophilic, but it can't fill the rafe, so it leaves. So that's the basic idea here. Okay? And if you calculate the forces involved that this can generate, they're enormous. The source of the stuff may be, there are two possibilities which I'll entertain later. One possibility is that the source of what were called crystalloid bodies, containing stuff that contains fibers and looks like they're being dumped into the rafe. Okay, so this is the capillarity model, and I call it the flame. Diatoms is the flame of life. Okay.
Okay. Dick, why is it pushing in one direction then? You got air down there in the bottom.
Excellent. I will give you 11 possible models, if you wish. Okay. I'm talking about the motor. You asked me about what controls the motor. Okay?
Okay.
Okay, and what controls the motor is unknown, but there are at least 11 hypotheses. Okay? Okay, here's another model which came up, let's see, who's this guy? A fellow named Smith, back in 1887. He looked at diatoms and he saw the shells opening and closing. And so he proposed that they act like a bellows, the kind of thing you use to blow air into a fire to give it more oxygen. Okay? And he made measurements and he saw the diatoms opening and closing. And as far as I know, he was ignored, and no one has ever repeated these measurements to see if diatoms do this. Okay? So he think they act like bellows, but the bellows, since they're self-contained, this would propel the diatom instead of blowing out stuff. And he presumed the stuff coming out was water. Okay. Okay. This fellow, Robert Lauderburn, coming up to 1896. This is a picture of him taken in 1928. He developed cross sections and showed the strange cross section of the rafe. He slits through the shell, okay, on opposite sides, and made a number of pictures of different types, or this, I think this is the shape of the rape at different positions along the shell. Okay, so it's quite irregular, but it's always quite bent. Okay. And he proposed that they were squirting out jelly and sort of doing jet skiing, what we would nowadays call jet skiing. Okay, this was supported by Otto Bushley in 1892, and okay, so we had that model. Now, come 1905. Okay, let's see, I got the names here. Daniel Jackson. Daniel Jackson decided that what makes diatoms go are bubbles. Okay, and he I guess he made little particles and with chemical reactions and showed that particles could move with bubbles, generating bubbles. Here I put two champagne glasses together to illustrate a diatom that has about this shape. He was absolutely sure he had solved the problem that diatoms make bubbles. Here's a fellow who was quite honest, and this is a translation from the French. I have no new theory to offer and see no reason to use those already abandoned. Okay? He threw up his hands. He was a medical botanist. Pierre Martins wrote this in 1940. And the curious thing is that he wrote one paper on diatoms, a very good one, reviewing lots of these old models. He threw up his hands, and when his obituary was written, the people who wrote it totally ignored his work on diatoms. Okay, so next, cytoplasmic screening, which was mentioned in the movie. The first model for cytoplasmic screening predated the discovery of motor molecules, goes back to 1943. And it assumed that you had some sort of protein that could stretch and contract. And this would then push the cytoplasm. This would be attached inside a cell. This would push the cytoplasm and make it move. So it's this mechanism is analogous to inchworm. Do you guys have inchworms in India? We have lots of them here in North America. I'm curious. What worms? Inchworms. They're called inchworms. Inchworms. English units. Otherwise, we'd have to call them 2.5 centimeter worms. Okay, so this model has been replaced by, as we understood, muscle and whatnot. Here is now a myosin moving, and guess what? It's rowing, acting just like a bunch of rowers. But this would be inside the cell. Okay, so we kind of come full circle. The old model of rowing, the diatom rowing, may involve internal rowing, this type. Okay? Now, how do you make a diatom with cytoplasmic screening? Here's the model for amoeba. And amoeba, the whole cell surface is continuously rotating, and if it touches a surface, it sticks to the surface, and then the the amoeba can move forward. Now, just imagine this thing in a glass case, because that's what diatoms have for their shells, a glass case, with something sticking out, and if you could imagine the whole cell membrane inside kind of rotating, you could see the possibility of getting motion this way. Okay, so cytoplasmic screening has been attractive, and what I did is reviewed in the chapter, I reviewed the various models for cytoplasmic screening, which, by the way, have been as crazy as the ones for diatoms. Also going to the we have some very specific models of how the myosin acts with the actin, or what actin filaments, which are also called microfilaments. Now, next thing I want to show you here is I started getting into the following. If the cell is putting stuff outside of the cell, that process is called secretion. And if you look at plants secrete something which we know quite well, which is cellulose. Now, cellulose is secreted at the cell surface. Let's see if I've got a better picture here. No, I don't. No. Okay, secreted by molecules that go into the cell membrane and then excrete or secrete these long chains of cellulose molecules. Now, cellulose are polysaccharides, and it's pretty certain that the stuff coming out of the diatom when it's moving is also a polysaccharide. So what I'm proposing is that there's a molecule similar to cellulose synthase, and which produces raphan, R-A-P-H-A-N, which is the polysaccharide involved in motility. So there should be then raphan synthase molecules. Now, for cellulose, you can see things are a little complicated here. The cellulose synthase is synthesized over at the Golgi apparatus, and then it is transported by myosins along actin filaments up to the membrane. So if you were to put chemicals in that disrupt the microfilaments, then the secretion of the cellulose would stop. So if this is a model for how diatoms work, you would then expect that the raphan synthase would stop being transported from the Golgi apparatus if you disrupted the myosin or the actin microfilaments. Now, the most popular model for how diatoms move assume, well, here's that model. This is the general model. This is the most popular model, which is you've got your microfilament bundle here, and it's attached directly to the RAF fibrils, which I'm calling raphan now, and those are then carried along the microfilament like a clothesline. Let's see if I've got it. I'll picture that later. Okay, that'll come up later. Okay, so in this model, you've got this whole sort of clothesline arrangement carrying the stuff over, and then it comes out. The capillarity and the hydrophobicity or hydrophilicity basically ignored this model. Now, here are pictures of those two microfilament bundles, which were in the movie, and they seem to be attached to these vesicles, and the vesicles maybe can be imagined to be carrying some fibril material. And indeed, if you have an F-actin means filamentous actin, which is the same as microfilament, and the myosin molecules can walk along it and they can carry vesicles. And this is well. Okay. So that's part of this model. Okay. Now, another curious model is by my friend Ryan Drum, and he suggested that diatom adhesion, they also stick to surfaces and slide along it, involves a suction cup, which he modeled with a toilet plunger. Okay? He's a fun character. Okay? Well, actually, the suction model was also done by the Harpers, Margaret and John Harper. They sent me their wedding picture, which was taken about the time they worked together. This would be 1967, when they worked together on diatom motility. And they proposed a model, indeed, where the diatom lays down a trail, and then it generates a negative pressure through the rafe, which holds it against the trail, and then it somehow moves along the trail. And so by analogy, I'm calling that the monorail model. Here's an old monorail train running on a single track. Okay? So it's kind of a weird model with them to put that much track and then hold on to it more. Okay, and I'll skip that one. That's the review of the models. Okay, next one. We're coming up to 1967. Ryan Drum proposed another model called the Colanda effect model. In this model, this is a cross section of an airplane, a gray section here, and if you have compressed air coming out of a wing, the compressed air will slide along the surface of the wing. That's the Colanda effect, and this creates additional lift and makes the airplane more efficient. Okay, so here I put a diatom on top of it, and the idea is the diatom, according to Ryan, pushes this stuff out, creating a Colanda effect and helps it move along. The only problem with this is that the Colanda effect requires very fast movement of the air or water, and diatoms aren't that fast. If you know some hydrodynamics, it's the difference between the diatoms are a low Reynolds number regime, whereas an airplane flies in high Reynolds number regime. So it's a model that really can't work this way, okay? But it's in the literature. Okay, another model which I'm throwing out here is by Lionel Jaffe, and this is not talked about times, but it could be, and that is that the cell can generate an electric current. The current will be generated by ions that flow through the cell outside and back in, okay? With pumping proteins in the cell membrane. So these kind of currents could be involved, especially in the direction question, Tom, you were asking. Okay? No one has looked for electric currents in moving diatoms that I'm aware of. Okay? Okay, so now we go back to the clothesline track model. One of the things about diatoms is they don't have to move on a flat glass slide. They can move over sand. In fact, they can push their way through sand. And here, Ryan Drum is indicating this by the stuff coming out of the race at various points touching sand grains. Okay? And here's a cross-section of the reef, and he's showing fibrils coming out and touching the grains here in cross-section. Okay? Okay, so here's the clothesline model. I've done it literally with clothespins here. Here's your actin fibril attached to myosin molecules, these blue things, which are attached to membrane proteins that synthesize the fluid, the fibers in the reef. Okay, so the clothespins would be rafan synthase, and these long string molecules would be the rafan. So here's a more classical view of it. Here's your actin filament, your myosin, what is called membrane complex, which I'm calling rafan synthase, in the cell membrane, carrying the stuff in the rafe attached to a substrate, and what moves it along is the motor molecules, these myosins. So that's the idea there. Okay. Next idea, 1987, diatom ion cyclotron resonance. This was a weird theory which had many papers associated with it, and it disappeared from the literature because when people tried to repeat measurements based on this idea, most of them were negative. So to sort of have this, taken the original patented image of a cyclotron, let's see, from 1934, and added some diatoms which are whipping around in the cyclotron. Nobody ever proposed a physical mechanism by which this would actually work. They just thought that they were getting effects on the diatom motility that they could attribute to. cyclotron resonance. Okay, another possibility is treadmilling. Now, treadmilling, this idea came up in 1998. Treadmilling is a weird idea. You've got a long molecule, and what happens is monomers are added at one end and taken off the other end, so that the whole thing is continuously moving as this process occurs. Okay, here's a chemical models for slow, fast treadmill. Okay, now in a treadmilling, you can also compound it by having multiple fibers here with myosins. Let's see. Yeah, you can also get treadmilling in this. Anyway, this one I threw in because you can see it's somewhat similar to the structure of bacillary, though at a molecular level where these things can slide against each other and create a large motion as a result. Now, one of the problems even with these with the cytoplasmic streaming literature is that the fastest molecule that's been observed is goes about 7 microns per second, but the fastest cytoplasmic streaming goes at about 100 microns per second. That typically run in 5 to 30 microns per second. Okay, now it's dogma in all of the diatom literature that diatoms can't swim. And this is actually unlikely because if they got rafes, a rafe will generate a current in the water if the diatom is just suspended in water, and so you expect some circulation around it in something like swimming. Okay, so here, this is for Tom and Susan. Here is my model or a sketch for a diatom bot. Okay, it's a submersible robot which has two pairs of pulleys. The pulleys are in a channel so that the outer part of this string here, which I'm modeling sort of bungee cord material, touches the water outside, top and bottom, and these will be rotorized that return, and this will generate currents outside. And then the purpose of the air is to make it neutrally buoyant so that this diatom bot could be checked for actual swimming without it sinking to the bottom. Okay? So that's a rough model for a diatom bot that can swim. Now, Thomas Harbinger has done a lot of work on diatoms that float up to the surface and indeed do swim at the surface of the water. He's observed them moving. And Thomas, I believe, is with us today. Okay, so I'm modeling this as here's the surface of the water, here's your diatom, and it's got a snorkel. Okay, so I'm pulling the snorkeling diatoms. So it seems contrary to dogma that diatoms do swim, though they may not be very efficient swimmers. Now, one model that's come up is acoustic streaming. If you have something vibrating in water, things will move next to it. If it's asymmetric in shape, they will move in a particular direction. So one model that's come up is about somehow people who propose this have proposed the diatoms vibrate. They haven't suggested how they do that, and then this allows them to move in water. So here is a jackhammer, which is a device for breaking concrete with a diatom jack. It's my model of how a diatom might move. Of course, the diatom will okay. Next model is Harbich, which comes out of the work I've done on this. On diatoms. This was with John Sabunko and Ali Beshchak, and Karina Menowak was involved in this. And that is the idea that diatoms, as the movie mentioned, they moved in a jerky fashion. They jump very fast, and the accelerations are enormous. And we came up with the idea that maybe what's happening is these fibers that come out when they hydrate explode, that they're explosively hydrated. So this reminded me of a model of how to undergo space travel that was done by Stanislaw Ulam back in 1946. And he designed a spacecraft which dropped atomic bombs behind it, and the force of explosion of the bomb just outside the ship would propel the ship forward. So it had repeated atomic bomb explosions out of space to propel it. Okay, so here's the diatom, which is with a bunch of fireworks behind it, which are accelerating in space. Okay. Now, one proposal was just last year is the diatoms can walk like geckos. The geckos have all this microstructure in their feet, and so I replaced the toes of on one foot of the gecko with a bunch of diatoms, because they also have microstructure. So we don't know if the gecko was inspired by the diatom or was the diatom inspired by the gecko. I guess we'll have to figure that out in the fossil record. Okay, so let's get into these models. Here's a detailed model of cellulose synthase, which plus each one of these little units here will be a synthase. Each one is produced in cellulose, and the cellulose is then combined into a bundle, which becomes the bundle of cellulose fibers outside the cell wall of a standard plant cell. Okay. Now, the interesting thing about this here, if we look at this one here, the synthesis is occurring here. One curious detail is that each of these individual cellulose fibers starts with 4 chitin molecules at the beginning. So one might look for chitin molecules in the raphe, the stuff coming out of the diatom, to see if it's analogous to cellulose in some way. Now, this stuff comes out of a channel in the protein molecule. Here's another depiction of it. And this channel would then protect it from water, which would keep it in a hydrophobic state until it gets outside. Okay? Now, in the diatom, outside is after you get through the raphe. So I suspect that what happens is that it's hydrophobic inside, and when it gets outside, it's hydrophobic. This is a picture of a diagram of an atomic force microscopy measurement of the forces with which you can pull on these fibers. That kind of works to that. Okay. Okay, now time to get directionality. Here's some stuff on directionality. If you, one hypothesis is that these microfilament bundles block these vesicles containing the raphe from getting to the raphe except at the ends. Okay, so this is one model. This is a picture of an etched diatom, which is kind of curious because it shows that the silica, which these are glass, the silica lining the raphe is much more compact than the rest of the silica in the shell. And this is what we suspect is a hydrophobic surface. Okay. In terms of transport, let's see, this is the detailed model of transport of stuff. One possibility is that these vesicles are secreted outside the cell, but underneath the shell, and then get out. So this is another option here. Okay, this is a model I proposed a while ago, and that is that this pair of microfilament bundles can actually slide and act as as switches, so that the vesicles containing the ribbon can only get in the ends. But if one end is blocked, here the right pore is open, so only at the ends can you get in, and then the diatom moves. The stuff moves this way, it's attached to the surface, the diatom goes the other way. Okay, so this is a proposal that these things actually switches. Now nobody's ever tested this idea. So okay, so here's what I'm coming to. A new working model which kind of combines a bunch of these ideas. This is a bubble film with gravity pulling down, and you can see the interference patterns show you that this stuff swirls and channels very nicely. It forms channels as it swirls. Okay, so if you imagine a cell membrane like this, carrying ray-fan synthase to the rays, which would be analogous to these lines here, then the whole surface of the diatom, this is the code you might be involved in the motility. Okay, so here's another cartoon from Edgar, Steve Edgar, surfing diatom. Okay, so here's the model. It's kind of a composite of everything that I've ended up with. Indeed, you have the microfilament bundle attached to myosins, which are carrying these vesicles, and the vesicles are now represented by the little surfing character. And these guys are surfing around the whole cell and then coming to the rafe, and they cause a cytoplasmic streaming in here, in addition, like this one, dumping its material into the rafe. But then what's stuck in is hydrophobic material, and the rafe acts like a wick, and the stuff comes out, and it produces an enormous force due to capillarity. So I put in this forward, stop, reverse switch here, indicating how the actin and the myosin may act in controlling the direction the thing goes. Okay, but the notion that this aspect switch, but it does not generate enough force to move the diatom. What generates the force is the capillarity. So in fact, there's a compromise between the models, and I had this one great paper which had this this phrase in it, may the capillary force be with you. Okay? So that's where I am. Okay? So it's a long saga. It's far from most of the components of these models have not been studied, and we're kind of stuck. All right, I got 4 minutes, so I guess time for questions.
Well, thank you very much. Let's see what the chat brings us. Not much. We just talked about inchworms. So, any questions from anyone? You have a little bit of time, so.
I had a question. This is Tom. So in some of these models, stuff comes out of the diatom, some of them it doesn't, right? Is there a way to like measure whether it's losing?
Well, for some diatoms, you can see trails that they leave behind.
Yeah, but if something's coming out, then there's less in on the inside, right? So how does it, you know, like losing, like getting smaller or something?
If you calculate the actual volume of the stuff, they can go for many, many minutes, and you'd hardly notice the change in volume. You see, the stuff that comes out, if I'm right about its nature, swells enormously. Thomas Harbich and I have done some calculations on this, but it swells enormously. So what you see in the stuff coming out is a much larger volume than the hydrophobic form. Because these things, when they swell with an enormous amount of water. I think I think it runs almost 99% water. Okay, so you know those toys where you have a little dinosaur model and you have water that flows up and it swells up?
Right, yeah.
Right, okay, it's similar to that. Okay? Another great example is the hagfish. It's a weird fish. If you disturb it, it suddenly produces enormous quantities of mucus around itself, which tastes awful and protects the fish from attack. Okay? But it's got to be the contact with water that swells this stuff up. Okay.
Any other
But
questions?
maybe that's, sorry, go ahead.
Oh, I was just asking if there were any other questions. We have like about 2 minutes.
Well, that sounds like salamander gel.
Yeah, well, another nice model for this is hyaluronate, which we have about 15 grams per each of us in at any given time. It's used for lubricant, and it also is a polysaccharide which swells up tremendously in water. And it's produced the same way. It's by hyaluron synthase, which is a membrane-bound protein, which only functions in the cell membrane. Yeah. So that's why the membrane model might be right, because all this stuff is probably synthesized by a Rayfan synthase that's somewhere or everywhere in the cell membrane.
So if it did exude this stuff and it expanded and it was kind of gelatinous, wouldn't the fibers get better traction if they were sticking into that and they could shove it backwards or shove it in one direction?
That happened. All you have to do is look at the candle. Candles burn at one end ordinarily. Okay, and so you have your directions supplied by the stuff coming in the wick at one end and burning off at the other end or along the length. But that gives you directionality.
Yeah.
Okay, so same here. If the diatom can control which end of the race the stuff comes out. And as I said, I come up with a list of 11 possible models for that. Then that's all it needs for the forward stop reverse behavior, which is the basic behavior.
Okay.
Do you have any references about the candle flame and the force that's produced?
Oh yeah. I've been having a lot of trouble with Word. I finished writing last night, and then Word started screwing up the format everywhere. So as soon as I fix what Bill Gates has wrought, I'll send Bradley a copy of this to distribute. Okay?
Thanks.
Okay.
Okay.
No more questions. Okay, go look for inchworms and Delhi.
Well, thanks, Nick, for presenting. I know you have to go. And I'd
Thank
just
you very
like
much.
to, yeah, thank you.
Okay, have a good day.
Yep.
Okay, bye.
Bye. So I'd just like to wrap up. Yeah. Just to mention that if anyone has, we'll follow up on this maybe in subsequent meetings. But if anyone has any, thing they want to present next week, let me know. Otherwise, I will be in, we can follow up on this in coming weeks. I know there was a lot of material. So, well, thanks for meeting and talk to you next week.
Okay, goodbye.
Bye.
All right. Yeah, I may not make it next week, but that's okay.
Okay.
Yeah.
Yeah. I mean, we like to be able to do things like asynchronously and offline. So if you want to do anything, if you have anything to contribute, you can present offline and I can present it in the meeting, or we can recap some of the things in the meeting. So.
Oh, okay. If I have a presentation that I'm preparing for something in university, that's relevant to this, I could pass it along.
Yeah, that would be good. Yeah.
Okay, Yeah, that sounds nice.
Okay.
Thanks.
Thanks. Bye.